Notice you have seen that before and this. We now turn our attention to the formula in section C, waves, sound and light. This section, waves, has these 5 formulae only, as required by CSEC for its physics exam. So we begin with formula 1. V is equal to F times lambda. In this formula, V is the velocity of a wavefront measured in meters per second. F is the frequency of the wave measured in hertz, and lambda is the wavelength in meters. So if we consider example 1, calculate the speed of a wave if its frequency is 45 hertz and its wavelength is 2.4 meters. Let's write down what we are given. We know the frequency, 45 hertz. We know the wavelength, 2.4 meters. We want to find its speed or its velocity. We know V is equal to F times lambda. So we just substitute the numbers we are given, 45 hertz times 2.4 meters, and we get 108 meters per second. Maybe CSEC will accept that, but to be sure, we have 2 significant figures here, 2 here. So let's round off to 2 significant figures, and that will give us 110 meters per second. And to express our answer even better than that, since we are rounding off here, that is the tens position. We take half of the tens position, which would give us 5, and we can better express our answer as 110 plus or minus 5 meters per second. This is also correct, but this is the format that CXC wants. That's question 1, fairly simple. Example 2, calculate the frequency of a wave if its speed is 654 meters per second and its wavelength is 0.0040 meter. Again, standard procedure, we write what we are given. Velocity 654 meters per second, wavelength 0.0040 meters, and we want to find the frequency. We know V is equal to F times lambda. If we make F the subject of the formula, we will get V over lambda, substitute these numbers that we are given, and we get a frequency of 163,500 hertz. Obviously, we have 3 significant figures here, 2 here, so we will have to round off to 2 significant figures, and we get 160,000 hertz, make it 160 kilohertz. Better still, since we are rounding off at this position, we take half of the tens position, which would give us plus or minus 5. This is also correct, but we will use that format for our answer. Third example, calculate the wavelength of a wave if its speed is 2.998 exponent 8 meters per second and its frequency is 4.6795 exponent 21 hertz. So we know the velocity, we know the frequency. We are asked to find its wavelength. Our formula says V is equal to F times lambda. We want to find lambda. So that will be V over F. We substitute the numbers we are given and we get an answer that says 6.40667 exponent negative 14 meters. So it's extremely small. Since we have, let's see, 4 significant figures here and 5 here, our answer can only have 4 significant figures. So we will have to round off 1, 2, 3, 4 at this point, which will give us 6.407 exponent negative 14. And this time it might be easier to just write correct to 4 significant figures. Of course, you can write this, which is a little harder to deal with. In this case, using plus or minus with the margin of error is harder to work out and to understand than just to say correct to 4 significant figures. I know I have been saying all along the line that CXC does not accept that, but in this case maybe they would. Now we come to formula 2. In this formula, F is frequency of the wave in hertz and T is the period of the wave in seconds. So let's look at the first example for this formula here. We know the period is that. We want to find the frequency. We have a formula that says F is equal to 1 over the period. Now understand that that one is exact. This one is exact. This is not one significant figure. That is 1.0000, as many significant figures as you like. We substitute in the formula and we get 22.222 hertz. We will round off to 2 significant figures, which is here. And so we get 22 hertz. That should be acceptable for CSEC. However, to be on the safe side, we could always take half of this ones position, which is 22 plus or minus 0.5 hertz. This, of course, is correct, but we will prefer to write it that way. Question 2, using this formula here. Calculate the period of a wave if its frequency is 2.34 megahertz. So we know the frequency is 2.34 megahertz. We need to carry that to hertz because we said the frequency is listed in hertz. We want to find the period. Period is equal to 1 over F. Remember, this one here is exact. So 1 over the frequency, and we get 4.2735 exponent negative 7 second. We will round that off to 3 significant figures, 1, 2, 3, and we get 4.27 times 10 to the negative 7 second, correct to 3 significant figures. Of course, if you want, you can work out the margin of error. If that is negative 7, negative 8, negative 9, and at this position here, where you're going to place that, half of that position will take us to negative 10. We get 4.27 times 10 to the negative 7 plus or minus 5 to the negative 10 second. As I said, using the plus or minus with the margin of error is harder to work out and to understand in these cases where you have exponent. Now we are going to look at refraction and the terms used, and to do that we will illustrate that by the use of a glass block. Consider this as a rectangular glass block, what you are seeing here. You have air on that side and of course air around here as well. If we draw a line perpendicular to that surface on the top there, of course it is called a normal. it is at 90 degrees to the surface of the glass block. Let us differentiate this boundary here, this air up here and glass down here, with that green line. Now if we draw a ray that touches at this point, we need to make sure we understand which is the angle of incidence. Some students would say that is the angle of incidence. Well, no, that is not it. The angle of incidence, well, that is the incident ray, and the angle of incident is the angle between the incident ray and the normal. So this angle here is the incident angle. This one here, not that one there. Now that light ray will pass through the glass block, and as it does so, it bends towards the normal. So this is now the refracted ray in the glass block. This is the angle of refraction, this angle here. Let us call it Y for the time being, and we will call that one up there Q. In such a case, Y is always less than Q. Now when that light ray reaches this boundary over here, let's show it in yellow, the opposite of what happened up here will happen down here. So now this ray that was the refracted ray up here, it's now the incident ray when we consider this boundary here, this yellow boundary. And so now this here becomes our angle of incident, or incident angle. And notice it is Y, which is that same Y up there, which means that these two angles are equal to each other because they are alternate angles with two parallel lines, those perpendicular, those normal. And then that ray exits here parallel to the original ray up here, and this is called a refracted ray at this point. And now this angle here is our angle of refraction, Q. You will notice that this is Q and that one up there is Q. That means that that angle is equal to this one. At this boundary here, this green boundary, N, which is the refractive index, is always greater than 1 because the angle of incidence will always be greater than the angle of refraction. That is when the ray moves from a less dense medium like air into a denser medium like glass. But when you come down here, the reverse or the converse takes place, where the light is now traveling from a denser medium, the glass, to a less dense medium, the air. And at this boundary here, this yellow boundary, the refractive index is always less than 1. So that total internal reflection can only occur when N is less than 1. In other words, total internal reflection can only take place at this boundary when the light is leaving a denser medium and traveling into a less dense medium, but it can never take place at that boundary because in this case the angle of incidence is always bigger than the angle of refraction. Alright, now so those are the terminology and we will use them as we go along. We are at this formula 3. N is equal to sine I over sine R. That is to say, N is the ratio of sine I to sine R. In this formula, we have a representation of Snell's law. N is the refractive index, I is the angle of incidence in degrees, and R is the angle of refraction in degrees. So let's look at our first example for formula 3. A light ray enters a glass block at an angle of incidence of 56 degrees and travels in the glass block at an angle of refraction of 42 degrees. Calculate the refractive index of that glass block with respect to the air. So we know that the angle of incidence is 56 degrees. We know that the angle of refraction is 42 degrees. What is the refractive index? N. Well, N is equal to sine I divided by sine R. We substitute the numbers we were given and we come up with 1.239. We can round that off to 1.2 because we only have two significant figures. Notice that N has no unit like kilograms or meters or seconds. It is a ratio and therefore has no unit. N is equal to 1.2. If you want to be a little more precise, you can say N is approximately 1.2 plus or minus 0.05. This is also correct, but if you write it like that, we can't go wrong for CSEC. Though this should be acceptable for CSEC. Let's look at example 2. A light ray enters a glass block from air at an angle of incidence of 46 degrees and travels in a glass block that has a refractive index of 1.23. Calculate the angle of refraction in the glass block. So we know that I, angle of incidence, is 46 degrees. We know that N is 1.23. We want to find the angle of refraction, which must be less than 46. So N is equal to sine I over sine R. If we make R the subject of the formula, R is equal to inverse sine of sine I over N. We substitute the numbers we are given and we get R, the angle of refraction, is 35.79 degrees. We round that off to two significant figures and we get 36 degrees, and that should be sufficient for CSEC. You can always add that, but I don't think that is necessary. This is also correct, but we will use that if we want to make sure that our answer is written the correct way. Example 3. A light ray travels through a glass block and exits into air at an angle of 76 degrees. If the angle of incidence at the glass air boundary is 52, calculate the refractive index of the air with respect to the glass block. So we know that the angle of incidence is 52 and that is in the glass block. We know that the angle of refraction is 76 and that is in the air outside the glass block. We want to find N. We are moving from a dense to a less dense medium. And so we find N is equal to sine I over sine R. We substitute the numbers we are given and we get a refractive index of 0.81. Now anytime you get a refractive index less than 1, that means that a ray is traveling from a dense to a less dense medium. Conversely, if you get a refractive index greater than 1, it means the light is traveling from a less dense medium like air into a denser medium like glass. So let's look at one more example here, and this one is a little difficult. The refractive index of a glass block with respect to air, so that's the air glass boundary, is 1.42. Calculate the critical angle if light is traveling from the block into the air, the other way around. So first of all, what do we mean by critical angle? Well, critical angle is that angle of incidence in a dense medium example glass, that will give an angle of refraction of exactly 90 degrees in a less dense medium, for example, air. So you can only calculate critical angle if the light ray is traveling from a dense to a less dense medium, because the angle of refraction will always be greater than the angle of incidence. So let's make a little drawing to make sure we understand what we are talking about. Let us say this is the glass block that we have here. Air on that side and air on this side. We have a boundary up here which is red, and to differentiate that one, we have another one down here which is green. So we have a light ray that touches this glass block at that boundary. Let us draw a perpendicular, a normal. That ray of light, when it passes through this glass block, will bend towards the normal like that, so that this angle here of refraction is less than that angle of incidence for the air glass boundary. N here we are told is 1.42. N at this of the glass block with respect to air. So it is in the glass from the air. The refractive index at this red boundary is 1.42. Now if we draw another normal here at this point, that light ray will go like that, and now this is our angle of incidence and this is our angle of refraction. Because the light ray is traveling from a dense glass to a less dense medium air, it bends away, it refracts away from the normal. So in this case, this angle here, this angle of refraction now at this boundary is greater than that angle of incidence. Well, the refractive index at this point will be the inverse of what we had up here, because when we were going from air to glass, the refractive index is 1.42. If we are now going the reverse from glass to air, the refractive index will be the inverse of that. So what we are doing here, we are going from glass to air, so it will be the inverse of what we had up here. So let's take that out. So what the question is saying is this: if that refracted ray were to make 90 degrees here, 90 degrees here, what will be this angle here? Find the angle of incidence when the angle of refraction is 90 degrees. Let us forget this piece at the top here for the time being and concentrate on this part down here. We want to find I, which is this. We know that R is 90 degrees, which is this refracted angle here. The refractive index of the air glass boundary is 1.42 up here, and therefore down here it will be the inverse of that, and so it would be 0.70. Having said that, the question becomes easy. We know that N is equal to sine I over sine R. We know N, we know R, and we want to find I. So if we change the subject of the formula and make I the subject of the formula, we get I is equal to inverse sine N multiplied by sine R. Substitute the numbers we are given. Well, the sine of 90 is 1. So in effect, you are finding the inverse sine of 0.70. And that will give us 44.427 rounded off to two significant figures, and we get 44 degrees. So we are saying that the critical angle here is 44 degrees. When that angle is 44 degrees, this angle here will be 90. So we get 44. We are saying when this angle here is 44 degrees, this angle here will be 90. So when you are asked to find a critical angle, it means what is the angle of incidence that will give an angle of refraction of 90 degrees, and that can only take place when you have light ray traveling from a denser medium to a less dense medium. Of course, if you exceed the critical angle, let us say 45 degrees, then you have what is called total internal reflection. Now let's evaluate this answer here. We're going to test it. If we find sine 44 over sine 90 and then inverse that, we should get back this, which is what we have here. So we know that our answer of 44 degrees as the critical angle is correct. So in this video, we learned how to use these three formulae: 1, 2, and 3. And this brings us to the end of Physics 16, Refractive Index.